Hello. Let me go ahead and post the assignments from this week. I'll give people a minute or two to get in. I don't see one person here so far. These are the assignments from this week. All right. So today, I wanted to say that I posted a link about a Zoom meeting today about college campuses, what those experiences would be like. So if you have time sometime today, actually it's Zoom, so it's live. You can go to that link and experience campuses. I want to say that the makeup quiz for static charge, that's in there. Don't forget that the quizzes are 35% of your grade, the same as performance tasks are. So if you didn't take the original, then you have received the makeup that is posted in your Google Classroom. I want to go over Coulomb's law today, and I know we had done that on Monday, but since Monday, I have graded the Coulomb's law quiz and the other assignments. I think it was the virtual lab on Coulomb's law that I was seeing a lot of misconceptions about Coulomb's law, or not seeing the point that we talked about, the comparison between Coulomb's law and Newton's universal law of gravitation. So I do want to go over that. Then we'll go over Ohm's law real briefly, and then series and parallel circuits. So let's start with Coulomb's law. So again, this is the list of the assignments for this week. We have Coulomb's law, PhET lab, that was due Monday. And again, anything that's turned in by Saturday, that's considered on time. Then this was a suggested assignment. So if you didn't do it, it doesn't count against you. This is study guide. Then we had the quiz on Wednesday, and that's an important assignment because it's a quiz. That's in the 35% of your grade bracket. Ohm's law, PhET sim, that's a lab. So that's important as well. It counts as a lab. So that's a 20% part of your grade. And then the extra credit is the only thing that you have for today. So let me go ahead and get a board so we can do Coulomb's law. It's still the top part of it. So Coulomb's law, we said, helps us find the force that's acting between two electric charges. So we have the force of the charge. Charge is the letter Q. So I'm putting a subscript as Q. So that's a label. That's not a variable. K, that's Coulomb's constant, times Q1 times Q2. So that's the charge on each of those. And divided by the distance between them squared. K is equal to 9.0 times 10. I want to say the ninth. Let me check. I don't have it. 10 to the ninth. That's newtons meters squared per coulomb squared. And now we have Newton's universal law of gravitation. We have force due to gravity, so that's a G for our subscript, is equal to universal constant times mass of one times mass of the second object divided by the distance between them squared. And G is equal to 6.67 times 10. I believe it's a minus 19th. I'm probably putting out bad information here. And that's newtons meters squared per kilogram squared. So do you see the similarities between these two? We have a constant here. Here is K and here is G. We're multiplying it by charge. We're talking about charge for this one. So we're using the product of the two charges and dividing by the distance between them squared. Here we have the product of the two masses. We're talking about gravity here. So the mass is what makes a difference divided by the distance between them squared. Now I know we use the small letter G for acceleration due to gravity for here, things on Earth's surface, but other places in the solar system, we have different planets. So the force due to gravity acting between those two things depends on the mass of the planet. And this universal constant is going to give us the force due to gravity that's acting on that planet. And in that way, because force is equal to m times acceleration, we can find the acceleration due to gravity on different planets. So this always holds true. The formula that we use using the small letter G, 9.8 meters per second squared, that's only for things here on Earth. But this is for everywhere that this holds true. Now, the two things that we want to look at, the size of this constant, this has 9 zeros after the 9 before the decimal point. This has 18 zeros before the 6 after the decimal point. This is tiny, 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 tiny. This is huge. Gravity is a very weak force. Force due to charge is a huge force. It's what makes our world what it is. It's what holds our things together so that they don't go flying through to the floor when you put something down on a chair or a table. It's that electric, the force due to the electric charge between them that holds them together. So this is Coulomb's law. This was the comparison that you were supposed to make at the end of the computer sim. All right. And this is really the big idea about Coulomb's law, is that the force due to electric charge is so much greater than force due to gravity. Now let's talk about Ohm's law. Let me see, I must have another board here. Oh, here, I have this one. That was about Ohm's law. So here we have a circuit, a very simple circuit with the switch that's open. So there is no flow. This switch is open, so there is no flow of charge through the circuit. This switch is closed, So we have a complete cycle here, a complete circuit. So we have the flow of charge. We have current flowing. So Ohm's law, we said that the things that make the difference are voltage, current, and resistance. We talked a little bit about those three things on Monday. Let's go into the idea that as current goes up, resistance goes down. I'm going to go get rid of the Coulomb's law one. Just finished writing on that board. So as voltage increases, and we've done similar things like this in the classroom before, but as voltage increases, that means that current increases if we're keeping resistance the same. Now let's take a look at keeping voltage the same. If current increases, then resistance has to go down. Otherwise, the voltage isn't going to stay the same. Let's do another one for voltage staying the same. If the current goes down, then resistance goes up. So we see that these two are inversely proportional. So voltage is proportional to current. Voltage is proportional to resistance. And resistance is inversely proportional. We have current is inversely proportional to the resistance. So that's 1 over resistance. And if we look at this equation, we can see that. So if we want to find out what current is, we have to divide both sides by R. So we can see that current is proportional to 1 over R. And the same thing with resistance. Resistance is inversely proportional to current. And they're both proportional, directly proportional to the voltage. All right. The resistance is really dependent on the voltage and the, no, the resistance is what we can change. I take that back. So let's go ahead and look at some circuits now. So let's get rid of, I guess we can get rid of this one. We haven't used this one since Monday. So I think we're good on this one. Oh, I left that there too long, huh? All right. So if we have two bulbs, we have more than one way that we can wire them. We're going to start with our battery. Let's put a bulb here. And we'll put a bulb here. This is series. In order to continue the path to get to the second bulb and to get back to our voltage supply. And remember, we said on, I think it was Wednesday, that we said it's the job of the battery. If this is a symbol for battery. It's a job of the battery to maintain a potential difference. So we have a short line on this side. That's a negative side of our battery. And this is a longer line on this side. That's a positive side of your battery. So there's a difference with the battery that we used on Wednesday of 1.5 volts between one side of the battery and the other. Without having a potential difference, there's going to be no flow of charge. Just like with water, if all the water is at the same level, so there's no potential energy difference from one place of the water compared to another, it's not going to go anywhere. It's just going to stay there. But when you have a potential difference, you have high water, and it's flowing down to a lower place, like in a waterfall, then you have a difference in potential, and the current is going to flow. The current of water is going to flow. It's the same thing here for our circuit. Now let's take a look at another way that we can line these paths up. So this is a one-way path. It's a one-way loop. But when we look at parallel, it's more like the rungs on a ladder. So we start with our voltage source at the bottom, and it gets to a point, and you can make the choice. Well, let's just say this is the battery. You can make the choice at this point right here whether to go through this, if we can draw one of those circuits. And again, we're using 2 bulbs. So here we get to this point. We have a choice and direction to go. We can either go through this bulb that's on this rung of the ladder, or we can go to this next one. That makes this a two-way path. This is a one-way path. And this way you have more than one way you can go. We'll just say 2. No, I don't want to say 2-way. It could be more than 2. So that's a big difference. You have more than one way to choose a direction. Now, in this one-way path, what happens if this bulb burns out? I'm sorry I can't demo this for you. I don't have, the only bulbs I have are those Christmas bulbs, and you can't connect those wires too much. So hopefully for next week, I'll be able to get some more. So when we get to this first bulb, we have to get through that bulb in order to complete the circuit. If this is burnt out, so if this isn't here, it's like having the open switch in the circuit and the path is incomplete what's going to happen to this bulb here? So this is not going to light. That means that if you have everything in your kitchen wired in series with each other, the plug for the toaster and the plug for the waffle iron and the plug for the coffee pot, if they're all wired in series to each other, if they all turn on at the same time, you're going to blow your circuit. You're going to have to replace the breaker or the fuse. Well, the breaker you have to switch, the fuse you would have to replace. So we don't want to do that in our houses. We want to have a better option. So let's take a look at parallel and see if this is a better option. So what happens if this bulb burns out? Does this bulb have a complete path? A complete circuit? Yes, it does. From the voltage source, it can get straight to this bulb and all the way back to where it started from. So that's a huge advantage of parallel versus series. Now there are other trade-offs as well. So in series, because you have to get through one bulb to get to the next, or whatever your resistor is, a bulb, a toaster, or refrigerator, all of those things are resistors in our electric circuits. In this circuit, the resistance is going to add up. So resistance adds up. And of course, the voltage will stay the same, right? So if the resistance, the total resistance is this plus this, then when resistance goes up, the current goes down, but the current is going to be the same everywhere. And the voltage is split. So the voltage has to be shared between this bulb and this one. I'm not going to go over any calculations of this because we're not going to cover that with my not being in the classroom with you. All right, so let's go ahead and take a look at in parallel what happens here. So we talked about this on, I think it was Wednesday, it might have been Monday, and we said that if we're waiting in line for the toll booth, if only one toll gate is open, there's a lot of resistance. It's really slow getting through that toll gate. But if they have 4 gates open, the resistance goes down. So the more pathways that we have, the lower the resistance. So total resistance is always going to be less than any one of these resistors. So your total resistance goes down as you add resistors. So the resistance, if this was 10 ohms and this was 10 ohms, the total resistance would be 5. it means that the voltage that's making it to here, it doesn't get used up before it gets to this one. It's the same as the voltage that's making it to the second one. So voltage is the same everywhere. But the current gets split up. So we have more voltage. Voltage is the pressure that's pushing the current along, but that means that the current has to be shared. The total current that you have for this circuit has to be shared between these two bulbs. I think that's all that I want to go over with this. Yeah. So here, when you have more bulbs, you have more resistance. Here, when you have more bulbs, your resistance drops. You have less resistance in parallel when you add up your two bulbs than you do here. Here they add up. Here, your resistance drops. You take out one bulb in series, the whole circuit goes out. You take one bulb out in parallel, or if it burns out, you still have electricity to power the other resistor or the other things in the circuit. If there are any questions, I don't see any questions. I only see 5 people here, so welcome. Thank you for coming. And have a great weekend. I'll see you next week. Next week we will go into electromagnetism. So we'll start Monday with magnetism and then add the electro part of that in. All right, I'll see you Monday. Have a good weekend. Bye-bye.